Hey, and welcome back to Integrated Science. I'm Miss Sparks, and today we're going to start adding on to our concept of motion. So previously we talked about scalar and vector types of models in which we can describe motion. Scalar is with just a numeric or a magnitude. So if I said that I ran up the street at 5 miles per hour, that would be a scalar. And then our vector had a direction. So maybe the street ran north. So I ran north. Today we're really going to break down our process of motion with speed and velocity and look at how we can actually describe it using our algebraic form. So I'm going to introduce one of our equations that we'll use quite a bit in this class. Hang on tight. You're probably going to want to get out a sheet of paper to take some notes. I will show you how to set up equations and use what I like to call a T-chart so that you keep everything nice and neat. Because as we move through this class, it will, some of the equations starts to piggyback off of each other, and you'll actually see that in our next episode when I start talking about acceleration. So let's kind of get started here. So speed in just general definition form is just a description of how fast an object is moving when you know how far it has traveled in an amount of time. So there's really two really important pieces of information right here. And that first one is how fast it's going. That's our speed. Oh, wow, that's bad. And we want to know a couple of different things. How far, which is our distance, and the amount of time, which is clearly a time measurement. So we're going to be using these two pieces of information, technically three. We're going to solve for speed, but we're going to figure out what was the distance an object traveled, what was the motion that it traveled in, and how long did it take to do that. And when we do that, that is once again our scalar. We are going to give it a magnitude or a numeric value. So if you want to think even back to qualitative and quantitative, this is a quantitative value that we're going to be using to help describe how things move. So speed is the distance an object traveled per unit of time. So kind of a smaller definition than this one up here. So once again, we still have distance and we still have time. So speed is what we use to describe motion, and one of the ways that we do that is by using this equation right here, which is speed is distance divided by time. So the D stands for our distance, which we kind of talked about just a few seconds ago, and T stands for time. So normally I'll have you set it up like this, which you will love to hate, and I am terrible at writing with this little guy, is what I like to call a T-chart. Something like that. And then we're going to fill in our magnitudes there that kind of help. I'm going to draw one over here too on my whiteboard, just so that you can kind of see it a little bit better in my handwriting. There you go. Speed equals distance divided by time. And in a minute, I'm going to pull some problems up and we're going to shove them in there. So this is the equation that we will use. So a pretty simple one. So in order to find speed, we need to know what is the distance and what is the time that it traveled. So there's two different types of speeds that we'll kind of go through as we move through this unit. Is the first one is just a constant speed, meaning that it stays the same all the time. And this is super unachievable here on Earth because we are always fighting a force that is always acting on us, which is gravity. So normally things here on Earth do not move at a constant speed. And you're probably thinking, well, Miss Sparks, technically cars have a cruise control that you can hit, and it does try to keep at a constant speed, but there are bumps in the road, there are hills, there are valleys, there are turns, and sometimes that constant speed can kind of be not as exact and stays the exact same all the time. However, if we look outside of our realm of the Earth and start to look at things that are moving in our solar system and then even in our galaxy and our Milky Way, then we actually can see things moving at a constant speed. So the easiest one to kind of think about is our day, 24 hours. Every day the Earth rotates one revolution around its axis. So it takes 24 hours to do that. We can also look at our calendars. It takes 365.25 days to travel all the way around the sun, and that's constant. That is something that is pretty standard. If something changes, then we're like, oh my goodness, we better start figuring out what's going on. But for the most part, it's a constant speed. So that has to do with just the idea is that there's other things that aren't getting jumbled up in the orbit of the Earth around the sun, or anything is coming too close to the Earth to cause that rotation to kind of become wobbly too. And when we get later in this unit or this year, we'll talk about how that actually can change. Jupiter and Saturn, they have some crazy things going on, and sometimes their rotations and stuff are just slightly different because there are gravitational objects that have mass that are changing them just ever so slightly. But here on Earth, things aren't normally very constant. So we normally use what is called instantaneous speed. It's a speed at a given point. So if you've ever been in a car and unfortunately maybe someone was going too fast or whatever it may have been, they might have gotten a speeding ticket. That's an instantaneous speed, a speed at a given point. We can also look at it for if you think about the Olympics when we're looking at track and field or swimming, those are normally instantaneous speeds. They're wanting to know what was the distance, what is the time that they traveled in, and so then we kind of figure out almost like an average, I guess, if you want to think about it that way. So what is it moving at that given point? That's instantaneous. So velocity is super similar to speed. In fact, we're going to use the same equation. If you jump down here, you can see it. Velocity is just displacement over time. Really, it's that distance. What has it been traveling over that time? However, we're going to use a vector I don't know why it keeps doing that, just ignore that. We're going to use a vector to describe velocity, which means we are going to provide a direction. So think back to our motion maps where we had our arrows pointing to the left or the right where the car was moving. We will use the same for whatever we are describing its motion. And so in this case, though, we can also say it moved north or south or up or down or wherever it may have been. So this is a little bit different versus speed because we're going to add another layer to it. So speed and velocity in this class are very, very, very similar. We'll use still our 3 points of distance and time. However, when we are asked to find the velocity, we will also provide a direction. So let's take a look here at what's happening with this physics teacher. So this is an equation that maybe we'll come across. So this one here says a physics teacher walked 4 meters east, that's important, 2 meters south, 4 meters west, and finally 2 meters north. And the entire motion lasted 24 seconds. Determine the average speed and the average velocity. So once again, we would make our little T-chart here. And I promise you, just join me on this journey of T-charts. They become really useful as we move through this year. So speed equals distance divided by time. And so now we're just going to plug in our information here. So time was easy. It's right here, 24 seconds. 24. Oh my goodness. I don't know why it keeps doing that. Just ignore it. I wonder if I can erase it. I'm sure I can. I don't know how. Oh, here it is. There. Haha. All right. And then let me get back to my pen. If we take a look at our distance here, we just have to add it all together. So 4 plus 2 plus 4 plus 2, 8, 10, 12. 12. So we got a distance of 12. So we don't know our speed. So all we need to do now is solve it algebraically. So once again, our equation is speed equals distance divided by time. And so all I'm going to do is plug these into my equation now. X, because we don't know speed. We do know D, 12. And we always want to put our units of measure behind it, meters. And it took 24 seconds. So now all we have to do is divide 12 by 24, and that's a half, a 0.5. So our answer is 0.5. Our units of measure are meters per second. So every meter that was traveled at 0.5 meters per second. So every one of those 12 meters, they were traveling at a constant of 0.5 meters per second. Velocity, we could just add to it because all it's asking for is what is its direction. So in this case, they were ending this way, which says north. So then we would just say north. So once again, I want you to get very used to setting up using what I like to call the T-chart and then plugging in our variables into the T-chart. Let's look at another one. So in 1985, Matt Bondi, whoever he may be, set a record for the men's 100-meter freestyle event in swimming. It took him 49.17 seconds, so there's our time, to swim the 100-meter length of the pool and back. What is his speed? So once again, they're looking for speed. And let's just kind of talk ourselves through this here. So, and we can see that right here. They're asking for the speed. So we're going to put our X right there. Once again, I don't know why. That's going to drive me nuts. It keeps us adding things. There. Back to the pen. All right, so distance. 100 meter length of the pool and back. So we have to double it. So 200 meters. And the time that it took to travel was at 49 and 17 seconds. So, oh my gosh, I'm not even going to fix that. You get the idea. So, same thing. We're going to plug it into our equation. X equals 200 meters. And we're going to divide that by the 49.17 seconds. And when you do that, you're probably faster than me because I'm not very good at writing with this little stylus. When you type that into your calculator, you should get 4.0, and I think it was like 6, 7, yada, 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 a whole bunch of numbers. We're just going to round it to the hundredths value. So 0.07, and that's our answer, meters. Because once again, they're traveling in meters per a second. I promise my handwriting's not this bad. So once again, all we did was go through and figure out what the speed was. We don't know the direction of the pool, so in order to ask for velocity. So we're just looking at speed here. And this is what we're going to practice with a couple of different simulations and tools, is how actually can we measure speed, and then how can we graph it out to show what it looks like on our graph using our X and Y variables. So hopefully that was helpful. Once again, speed is scalar. Velocity is a vector with a direction. Both, we're going to use the same equations, which is, and I'll even write them over here so you can see that my handwriting is not of a toddler. And velocity. So we're going to be using these two equations with our T-chart. That's the big thing that we're going to be working on, is using that T-chart to show our work, which is always really important. So hopefully that was helpful, and I look forward to seeing you again.